Computer. So, good morning. My lecture today will be about nanomaterials from synthesis to applications. I will try to show 3 examples, but you are free to stop me in the middle if I take too long. So, nanotechnology is the area of science that deals with the synthesis, the chemical and physical characterization, the manipulation or assembly, and at the end the applications, the fabrication of devices using nanoscale materials. We can define nanoscale materials as zero-dimensional nanoparticles. All the 3 dimensions are less than 100 or 200 nanometers. One-dimensional materials, my lecture today will be focused on one-dimensional materials, nanotubes or nanowires. Only one of the dimensions, the diameter is less than 100 nanometers. They can be very long, microns length. They can be 2-dimensional or 2D materials, which are films with small thicknesses. The research efforts in nanotechnology can be divided in 3 main groups: the synthesis of new nano building blocks, the manipulation or assembly of these building blocks on surfaces, and the last one is the applications or the fabrication of devices, medical devices, sensing devices, optoelectrical and electrical devices, and so on. I will try to show 3 examples, and the first example will focus on the synthesis of a new generation of nano building blocks, silicon, crystalline, single crystalline silicon nanotubes. We can see here a general schematic that describes the general synthetic method. The first step consists on the deposition of gold nanoparticles or any other type of metal nanoparticles. Those gold nanoparticles serve as catalyst sites or catalyst seeds for the growth of germanium nanowires. I will show later on why we use germanium. We grow by a CVD or chemical vapor deposition system that we built in our lab. We grow germanium nanowires. The next step is the deposition of a silicon layer or a silicon nanolayer on top of the germanium nanowires. The last step is the removal of this core shell, germanium core, and shell, silicon shells. The removal from the substrate, from the growth substrate by sonication. We make a suspension in a liquid. And the last step consists on the dissolving or the chemical etching of the interior germanium cores, leaving behind intact silicon nanotubes. You can see here a low-resolution transmission electron microscope image showing that we can actually synthesize a very nice, high-quality silicon nanotubes. It looks very easy, but there were many challenging steps here. In order to create single crystalline silicon nanotubes, we need to make sure that the core material, in this case germanium, is morphologically similar to silicon. So germanium and silicon are very similar morphologically because they have a 4.2 or 4% lattice mismatch. So silicon can grow heteroepitaxially on germanium. It means that silicon can use the germanium crystalline core or germanium nanowire and can grow on it not in an amorphous way but in a crystalline way. But silicon and germanium are not only similar from the morphological or crystalline point of view, they are very different from the chemical point of view, extremely different. So we knew in advance that we can take a silicon shell, germanium core nanostructure, and only by dipping it in a hydrogen peroxide solution here in the last step, we can dissolve the interior germanium, leaving behind a silicon wall which is single crystalline and intact. Nothing happens to the silicon in the presence of hydrogen peroxide. So the technique to grow the germanium nanowires is called a VLS, a vapor liquid solid mechanism, that was found in the 60s for the synthesis of silicon whiskers, large silicon whiskers. And this technique is based on the use of nanoparticles as seeds. As we can see here, we deposit the nanoparticles, as said before, on a surface. Then we introduce that in the CVD system, chemical vapor deposition system, in my lab. At the right temperature, what we call a temperature higher than the eutectic temperature. We create a liquid droplet in the presence of the silane precursor or german precursor. And after we get to a supersaturation, silicon or germanium starts to precipitate inside this liquid alloy droplet, and the nanowire starts to grow and grow and grow and grow, and we can make nanowires of hundreds of microns, even millimeters long. By modulating or by controlling the size of the nanoparticle, we can control the diameter of the nanowire. That's a known science. That's not something that we invented in my group. So here we can see the first results. This is a germanium nanowire. We can see high resolution image showing the high crystallinity of the nanowire. This is actually, each nanowire is a single crystal. And there are very few defects, if at all, along the nanowire. The second step is the grow or the deposition of a silicon layer, and we can clearly see here in this high resolution transmission electron microscope image that the silicon layer follows the crystal planes of the germanium core. So we can see the difference in contrast. Then by dipping the nanowires, this core, germanium core, silicon shell nanowires in hydrogen peroxide, we get high quality single crystalline silicon nanotubes. And we see here that by controlling the size of the gold nanoparticles that we used at the beginning to generate the germanium nanowires, we can create different tubes with different internal diameter. So we have almost a perfect control over the internal diameter of the nanotubes, 10 nanometers internal diameter, 20 nanometers internal diameter, and here 40 nanometers internal diameter, and we see that the nanowires are very similar, the nanotubes in the same sample are very similar in dimensions. We can also control, by controlling the time of silicon deposition, we can control the wall thickness of the nanotubes. So we can do nanotubes with walls of very small thicknesses down to 1 nanometer, or very thick thicknesses of tens of nanometers. But there are limitations to this technique, and there are two basic limitations. We cannot grow germanium nanowire cores. And I would like to call the germanium in this case a sacrificial material. Why is sacrificial? Because we use it as a template to create a tube, and in the last step, we dissolve it by chemical etching, leaving behind the silicon nanotube. But the limitation is that we cannot grow germanium nanowires bigger than 60 nanometers in diameter, and we cannot grow germanium nanowires smaller than 5 nanometers diameter. And the reason is that very large gold nanoparticles, when we heat them up at temperatures higher than 350, 400 degrees, they tend to split up into smaller particles. So each particle comes from a single larger one, and each one can grow a single nanowire of germanium of a smaller diameter, or a single nanoparticle, because it is very large, it can serve as a multi-site growth seed. And actually we have a single large nanoparticle, and from it we see very small germanium nanowires growing from a single one. So we have to look for ways in order to create tubes with larger diameters and tubes with smaller diameters. Here we can see how we create tubes with ultra-large diameter, and I want to emphasize those silicon nanotubes that we see in those images are single crystalline. And we found out a very, I think, ingenious way to do that. We took the germanium nanowires of 20 nanometers that we know to do very easily, and then we deposit epitaxially a germanium layer in situ that enlarge, make this nanowire fatter and fatter and fatter. So we can control how this germanium nanowire gets larger and larger with time. Then we deposit the silicon layer, and at the end we dissolve the interior germanium, and we can get, this is pretty amazing, we can get silicon nanotubes, crystalline silicon nanotubes with internal diameters of 60 nanometers, 150 nanometers, and half a micron. I think this is the first example that shows how we can control over all the dimensions of a nanotube by a single universal technique, because we use the same technique, and everything is done in situ. And then we found a way in order to create ultra small diameter nanotubes. And we took the 20 nanometers diameter germanium nanowires, and it was actually very challenging how to etch germanium. The etching of germanium is not so easy as the etching of silicon. Germanium can adopt many oxidation states when you try to oxidize it or when you try to etch it chemically. So each spot reacts chemically in a different way. So in some areas, germanium can etch faster than other areas. So the oxidation front of a germanium layer is not as smooth as a silicon layer, but it is a little more rough. And we can see here the images that we oxidize the germanium in the first step in the presence of oxygen, and we create here a layer of germanium oxide. We knew also that germanium oxide is very different than silicon oxide. Germanium oxide, just by heating it at temperatures higher than 450 degrees, volatilizes. It vaporizes. Silicon oxide is pretty stable up to more than 1,000 degrees Celsius. So we oxidize the nanowire at different extents. We vaporize the germanium oxide. We deposit a silicon layer, and we get nanotubes of very small internal diameter. We get nanotubes of internal diameter down to 1.5 nanometers. This is almost the diameter of a carbon nanotube. And I think this is the first example of an inorganic crystalline tube with dimensions as small as carbon nanotubes. And this is, I think, pretty remarkable. In addition to the control over all the dimensions of the tubular structures, we have also a control over the shape, using the same approach. And we knew that we can control the shape of the germanium cores by controlling the temperature during the growth of the cores, and we can create conical structures. We can see here in the next slide how the temperature of growth of germanium nanowires in the CVD setup controls their shape. At low temperatures of 280 degrees, the germanium cores, sacrificial nanowires, are really nanowires with a very homogeneous diameter along their length. But at higher temperatures, we have two processes. One process is the elongation of the nanowire, or what we call the axial growth, catalytic growth, coming only from the nanoparticle outside. And we have a second chemical process at higher temperatures, which is the pyrolytic decomposition of germanium and the position of germane on the walls of the nanowire, of the growing nanowire. So we have a radial enlargement of the nanowire and at the same time an elongation. So the areas of the nanowire which are exposed longer times in the setup get fatter and fatter and fatter. So we can control by the temperature, we can control actually the tapering angle of the cones. We can get cones with smaller tapering angles and cones with larger tapering angles. And we can get, by this way, hollow, completely hollow, high-quality single crystalline silicon nano cones or nanotubular cones. And this is the first example of nano cones with such a control over the dimensions. It's not only important to control the dimensions and the shape, but the same technique allows us to control also the chemical composition of the walls. So we can, by using impurities, like what we call dopants, like for example boron or phosphorus, we can create silicon nanotubes with a controlled doping ratio on the walls. So those nanoscale materials will be excellent candidates for the fabrication of electrical devices, and we can see here a nice field effect transistor. We see the nanotube, silicon nanotube, doped with boron, 2 electrodes, source and drain. We use the gate electrode, the wafer itself, what we call a back gate, and we can see the electrical response of this field effect transistor. It behaves as a P-type transistor. Negative voltages lead to higher currents. Another nice thing about these nanotubes is that the nanotubes can be chemically modified. Unlike any other type of nanotubes, we can modify the interior and the exterior of the nanotube independently, completely independently. And why is that? Because you need to remember that those tubes started from a core shell structure. So the interior part of the tube was filled with germanium. So instead of dissolving the germanium, we can modify, in the first step, the exterior wall of the tube with an hydrophobic or hydrophilic chemical reagent. And then by dissolving the germanium, we can modify the interior wall with an hydrophobic or hydrophilic reagent. And thus we can get nanotubes which are hydrophobic inside, hydrophilic outside, or the opposite. Those materials are very important because for drug delivery, for separation of materials, for dissolving organic molecules into water solutions, or dissolving water-soluble materials in organic solvents. So we are trying today to get some applications using those electrical devices and those silicon nanotubes for some drug delivery experiments and some nanofluidic or nanoseparation or counting of biomolecules. Remember that those tubes, and if I go back, those devices are not only field effect transistors, but we believe that we will be able to see molecules or biomolecules flowing inside the tube by only reading the electrical properties or electrical signals of these field effect transistors. So we believe that we will be able to count proteins like a nano flow cytometry. We used this basic approach for the synthesis of silicon nanotubes in order to create nanotubes of much larger complexity. What we call a tube-in-tube, sorry for that, nanostructures. So the basic idea is to take the first generation of germanium nanowires, to make a first generation of silicon shell, and then again, a second generation of germanium, and a second generation of silicon, and so on, so on, so on. And then dissolving the germanium interlayers, we can get tubes inside tubes. We may call them multi-wall silicon nanotubes, but I wanted to make a difference when we call those materials. Carbon nanotubes, or multi-wall carbon nanotubes, or boron nitride nanotubes, we cannot control the distance between the walls. We cannot control the chemical composition and the dimension of each wall. In this case, by controlling the size of the germanium interlayers, we can create walls with a perfectly controlled distance between each tube. And we can create silicon walls with each wall having a different chemical composition and a different dimension. So we can see here, it was completely not easy to get to this point. It was very, very difficult. Although silicon and germanium has very similar lattice parameters, they still have a very different thermal expansion coefficient. So when you are talking about nanoscale materials, the deposition of silicon and germanium goes through a mechanism that is called Stransky-Krastanov. It doesn't go directly as a layer-by-layer deposition mechanism, but it goes through an island growth because of the stress that is formed on the germanium layer. So we had to find ways to overcome this limiting mechanism. And I think my student, I will talk about that later, worked for a very long time, and she found a condition, I think the only condition in the world that can create a germanium layer that does not form these rough, ugly layers. We don't have time to talk about that, but we can see here what we get from that. We get double-wall silicon nanotubes. We can control the distance between the walls, between 2 nanometers, 12 nanometers, 30 nanometers, 65 nanometers. That's why we call them silicon tubes in tubes, and not just multi-wall silicon nanotubes. Also, we can imagine about building electrical devices of much higher complexity. We can take a single nanotube with 2 walls, and by a particular process, We got help of Alex in the e-beam lithography. We can make electrical contacts with each one of the walls of the same nanostructure. So let's imagine that we have a nanotube with an interior tube that is N-type doped, while the exterior nanotube is P-type doped. By using the same nanostructure, we can create electrical devices that have a dual functionality, electrical functionality. And we can see here that the inner tube gives results of an N-type transistor, while the outer tube gives electrical results that fits a P-type transistor. So the same volume, the same nanostructure with the same volume can give us many different electrical devices at the same time. We can create nanotubes with a larger number of walls, a tube in tube in tube. And we can also create other type of nano building blocks. Instead of being a tube inside the tube, we can create a silicon nanowire material inside a silicon nanotube. Those are structures which were not seen before. So we are playing around to create new nano building blocks with new nice properties. So in conclusions of this part, we can create silicon nanotubes with full control over all the dimensions, all the chemical compositions of the walls. We can create silicon nanotubes-based electrical devices. And now we are moving onto some of the applications of those silicon nanotubes. And I would like to move fast. How long do I have yet? 8 minutes. Okay, 12. So the next application or the next work that I would like to show deals with the assembly of nanowires. Why it is important to assemble nanowires? Because at the end, what we want to do with those nanoscale building blocks is to build electrical devices or any type of devices, and we need to take these wires and to connect them to the external world electrically. So we need to know where the nanowire is sitting on the surface. First of all, I need to know exactly where this nanowire is sitting on the surface, what are the exact coordinates of the nanowire. So when we take a surface and we spread nanowires, then we don't know where each one is sitting. We need to look for each one, like many guys are doing now. Each one we are looking individually. We are connecting the nanowires with 2 electrodes to the outer world, and then we go to the next nanowire and next nanowire. So this is not the way to get into any applications. So there are 2 techniques in order to assemble nanowires. The one is growth and place, and the other one is growth in place. So the growth and place requires to grow a nanowire on a substrate, remove it from the substrate, and then put it on a surface. So we need to control how to manipulate the nanomaterials in order to make each nanowire to sit wherever I want to be. And the second one is the growth in place. So our technique is related to the growth in place group. So one technique is just to drop the nanowires on a surface, and they will be randomly deposited. We need to look for each one. We don't have any control over the coordinates of the nanowires. Other techniques that control the orientation of the nanowire are the flow alignment. So we take the solution, we flow them, and the nanowires align along the flow direction. The other one is by Langmuir-Blodgett. Langmuir-Blodgett are 2 plates. The nanowires are sitting in the interface between the water and air interface. So when we press those 2 plates, the nanowires align perpendicular to the pressure that we applied. And then we dip our surface, and we get a moderate control over the orientation of the nanowires, but we don't have such a good control over the density, over the length of the nanowires. And the other technique that is a much more recent technique, instead of requiring to remove the nanowires into a solution, they grow nanowires on a surface, and they dry transfer the nanowires. They just slip one surface over the other, and the nanowires break when we slip the 2 surfaces. They break randomly along their length. This is one of the limitations. But this technique gives an easy way to create oriented surfaces with nanowires deposited on it. Our technique, and I will move directly into the results, our technique is based on the growth of large-scale silicon nanowire arrays. How do we do that? By a top-down approach. We take a silicon wafer, we put masked metal masks. We can see here we take metal masks, metal dots, and we etch chemically the wafer. So wherever we have a mask, the wafer is not being etched. So then at the end, we get by dry etching, by a technique which is called deep reactive ion etching, we get almost perfect arrays of silicon nanowires. We know exactly where each nanowire is sitting. By controlling the dimensions of the mask, we can control the diameter of the nanowire. By controlling the time that we do the etching, we can control the length of the nanowire. We know exactly, first of all, where it is sitting, where it is standing. The next step is controlling the density. We can see that we can control the density of the nanowires, and the length, and the diameter. So we have a full control over each one of the nanoelements. The next step is how to bring those nanowires down. What we call how to planarize the nanowire elements. Not only how to planarize them and prevent that those nanowires during the planarization step will be dragged away from the place where they were attached. At the end, I want to know where each nanowire is lying on the surface. So we found out a very simple approach that we call it a knockdown. We use a rolling material, a PDMS, hard-baked PDMS material, manually roll it on the surface, and we see that the nanowires are knocked down, and sorry for the resolution, but the nanowires are knocked down. This bright spot is the place where the nanowire grew at the beginning, and we can see each of the nanowires being on the surface. We have very little amounts of failures where nanowires are being removed from there. So this technique is very nice. Using harder materials cause the nanowires to break randomly, and the nanowires are also removed away from the surface. We also invented a different way to facilitate the breaking down of nanowires. We found a way to chemically etch only the base of each nanowire. This technique we call a point of easy break. We knew that if we only etch and make the diameter smaller at the base, then when we planarize them, they will break only at their base. This is a weak point. So we can see here that we can build devices with 1 nanowire per electrical device. We can control the number of nanowires per electrical device, 2 nanowires per electrical device. And those electrical devices are very similar because they were done on the same wafer. They are almost exactly the same dimensions, almost exactly the same chemical composition. And I will take 2 minutes, only 2 minutes more. This is my student slide, how to make applications using silicon nanowire devices. And in this case, the application, I will just move fast into the results. We use those arrays of silicon nanowires as highly selective and sensitive sensors for the detection of explosives, in this case TNT, trinitotoluene. We simply take a silicon nanowire electrical device, those devices, a large array of nanowires. We modify the nanowire with a layer of aminosilane, so we have a nanowire modified with amino groups. We knew in advance that amino groups are good electron donating groups that can interact strongly with trinitotoluene. Trinitotoluene is a strong electron accepting molecule that can make a charge transfer complex on the surface. So by interaction of these gas molecules, explosive molecules with the surface, we expected to get a complex. This complex, after the charge transfer happens, we get a negative charge on the surface that was not present there before the interaction between the two elements. So then we expect to be able to read with high sensitivity those negative charges that are created on the silicon nanowire devices upon the interaction or upon the recognition of TNT. So this is the electrical characterization of the devices, and we can see here that interaction of the surface or the electrical devices with different concentrations of TNT lead to higher and higher and higher signals. We have a clear concentration dependence of the sensing. The sensing is not also extremely sensitive, but is also extremely fast. We can see that the interaction of TNT leads to almost an immediate signal change or electrical signal change. and we can sense TNT with the most sensitive devices down to the half femtomolar. Half femtomolar, it is a detection limit that is orders of magnitude more sensitive than any dog outside there, without all the limitations of dogs. We also have limitations. I don't want to say anything bad about dogs, but this sensing device is also very specific and selective for TNT. Other materials almost do not give signals or give smaller signals. We are now trying to modify the surface with different amino groups, each one having a different electron donating characteristics. So, yeah. So we will have actually like an electronic nose for the sensing of different explosives. And one of the important things is, first of all, most of the sensors behave almost the same. The sensors are very stable over a long period of time. And at the end, those sensors can detect not only in solution TNT, but directly from the vapor phase. So we can collect air samples or vapor samples containing TNT, and the dry sensors in air can detect the TNT, because this reaction of charge transfer between the amino groups and TNT occurs also in air. And at the end, I want to thank to all of you for being here, and to all my group, especially to Moshit, that she's a PhD student in my lab, that she was involved in all the nanotubular synthesis, nanotubular structure synthesis, to Yoni and Roy, both of them PhD students working on all the sensing experiments, and Alex and Tamir, a PhD and a master student that worked mostly on the assembly of nanostructures. And that's all. Thank you. Not yet. Not yet.
Because I think they will have very interesting
the nanotubes?
I think they will have very interesting collaboration.
You mean the nanotubes?
Yes. So when you have this array, this order array.
Yes, we didn't check. We didn't check. We actually don't have the experience also and the knowledge, so we concentrate on what we know and try not to enter into other fields. Okay?
In the tube inside of tube configuration, what maintained the spacing between these two tubes? Why did they just short out?
Yeah, that's first of all, that's an excellent question, and after seeing all the images, we ask all the time why they are not touching. We know that when you expose silicon to the atmosphere, to oxygen, to air, it creates a native layer of oxide, silicon oxide. Silicon oxide is negatively charged because of the presence of silyl groups there. So there is an electrostatic, it must be an electrostatic repulsion between the walls. The walls do not, that's a fact, they do not touch. What we have seen is that for tubes having a larger distance between the walls, then the inner tube over long distances can bend. And you see the inner tube bending. Even you saw that in some of those images. The inner tube can bend, but it never touched the outer tube. So they repel each other electrostatically.
How many layers of silicon are there? How much of it is oxidized?
That's a good question. The silicon oxide native, the native thickness of the thickness of native oxide is between 1 and 1.5 nanometers. So we can get walls down to 2 nanometers, still keeping them silicon and not silicon oxide to some extent.